Thank you very much for the introduction, and thank you for this opportunity. I'm very much looking forward to interacting all kinds of people from all fields. So I'm a condensed matter physicist. So today I will talk about this higher Berry phase, and then its formulation using tensor network. And then I will also present sort of quantum field theory framework to discuss a higher Berry phase. So this is the, I have a series of works with my collaborator Shuhei Oyama, who really did all works. I learned a lot from him. And then this most recent work, we deformulated everything using the language of boundary conformal field theory. So I will first present tensor network story, and then I will move on to the boundary conformal field theory aspect. So what is higher Berry phase in the first place? So the higher Berry phase is the some sort of generalization of the regular Berry phase in quantum mechanics to the many-body context or quantum field theory context. So quantum field theorist, higher Berry phase is very closely related to, almost equivalent to Wess-Zumino term in Wess-Zumino-Witten theories. I think it can be somewhat broader, but I think for the zeroth order approximation for field theorists, it's Wess-Zumino term. I think recent advancement really came from the kind of in the many-body physics, kind of broader many-body physics context, for example, using tensor network and so on and so forth. But anyway, I first present this discrete lattice formulation, and then I will come back to this quantum theories perspective. Another question you may have, what do I mean by higher? So higher here means, I think the details I have to present later, but just a quick overview is the regular Berry phase. We have a Berry connection, which is one form. But for higher Berry phase, we could have higher form gauge field. And then there's some, so to speak, the higher structures we can discuss. So that's what we mean by higher, but I think I will try to explain. But let's start with the regular Berry phase. So this is a Berry phase in quantum mechanics. So the setting for the Berry phase is I have a quantum state psi, which depends smoothly on some parameter. I write it as x. X can be can have some multiple component. And then we change, for now I don't consider degeneracy. I will change this parameter x smoothly, and then we will see what happens. We can also draw a picture like we have some manifold M. So this parameter can be a point on this parameter M. So we can call this M be a parameter space. And then we pick some point x. And then at each point x, we have this quantum state psi. And then famously, quantum state psi has a overall phase ambiguity, or maybe redundancy, which plays an important role. So the overall phase, somehow it seems almost unobservable, but phase we accumulate as we change x smoothly on M. So there may be some loop gamma. It has some consequence. And so this phase we accumulate along this loop gamma can be computed by taking, if I parameterize this gamma by some parameter t, I have a one parameter family. So this is a phase we accumulate, or I times, this is a phase we accumulate along this loop. So this part is we can write this part as using one form. So this is the Berry connection. Berry connection. Okay, maybe I put dt here. Yes, so this is the familiar story. Basically, we want to generalize this to many body physics context. So psi is going to be some many body quantum system. But before going to many body state, I also want to mention topological aspect. So what we are discussing here is a family of state. So this is the not just a single state, but I have a parameterized state. So it is a family of state defined on the parameter space. Yeah. Kind of familiar question in condensed matter physicist, or familiar question in many body physicist, is that for a given state psi, is there topological distinction? For example, we could discuss different phases of matter. So it is a very popular topic in condensed matter physics to classify different kinds of phases topologically. What kind of quantum phases we have? We could also ask similar question for a parameterized family of state. Okay, so is there topological distinction among or between different parameterized family of state? Okay, so for the case of Berry phase, we can define a topological invariant for a family. So this is the integral of the curvature. I put 2 pi here, or this is the f is dA. So this is integer, which basically measures the magnetic monopole in parameter space. This is Chan number, Chan integer. So this is a topological invariant which you can assign to a given family. So if you have a different family of state, and if they have a different quantized integers, they are topologically distinct. So this has many applications in condensed matter physics. For example, famously, Hall conductance in quantum Hall effect, it can be represented. It can be represented as the Chan integer, Chan number, which defines for a given particular state. But there's also the similar example, which is called Sauer's pump. Sauer's pump, where we have a family of quantum many-body states, which depends on the parameter. But you can assign a topological invariant for the adiabatic process. And for each adiabatic process, if they have a different integers, these processes are topologically distinct. And the canonical example would be Sauer's pump. Okay, this is example. Another I think equivalent perspective is that we can look at the topological classification of fiber bundle or complex line bundle on M. So this is characterized by a integer cohomology class. So this is called Chan class. Chan class. Okay. So this is a very quick overview of the regular Berry phase, and then topological aspect associated to this. So idea that we generalize this somehow. And then, yeah, by the way, please interrupt anytime. So quick overview is that, or yeah, maybe I should also mention the kind of idea I will use very often later. So this is the idea by Wu and Yan. So on the one hand, we can see topological distinction from the topological invariant by integrating over curvature. But there's a kind of maybe not completely different, but alternative way to look at it. So if you have a parameter space M, wave function, in particular, the gauge of the wave function may not be defined smoothly over the parameter space. That is the case when you have a non-zero Chan number. So we start to patch, anticipating some problem of covering the whole space using the single patch. We start using patch to describe these states over this parameter space. So maybe I can draw additional picture. So global picture may be looking like this. So I have a parameter space M, but I cover parameter space by using here by two patches. Let's say U alpha for northern hemisphere and the U beta for the southern hemisphere. And then if the this Berry flux or Berry curvature is non-zero, there's a flux going through this parameter space where I'm pretending it looks like a two-dimensional sphere. And then there's a Dirac monopole inside this parameter space. So famously, Dirac monopole has a Dirac string, which is somewhat singular configuration. But you can avoid singular configuration if you patch your parameter space. So your wave function is smooth for this each patch. But something interesting happens when these two patches overlap. So this is the intersection of U alpha and U beta. Okay. So when these two patches overlap, there are now two wave functions, two quantum states we can talk about. Psi of alpha, which we defined for the northern patch. And the patch is, within this patch, wave function is smooth, so you can just continuously move on this patch. But then near the equator, you get this wave function psi alpha, maybe here. But there's another state, psi of beta, which comes from the southern patch. Okay, and then when these two patches intersect, now you have two wave functions at single point here, some point on the equator. Okay, so anywhere on the equator, you have two wave functions, psi alpha and psi beta, and they must be physically the same because I'm just talking about the gauge choice. But up to gauge choice, these two wave functions are the same. So therefore, these two states are related by overall phase factor, which I write as phi alpha beta. So from here, so this is something we may call transition function. So from the transition function, we can reconstruct the topological data of the parameterized family. So I have this phase phi everywhere on the equator. And then if there's non-zero Chan number, this phase has the winding number along the equator. So that's another way to see there's something topological in this setting. So that is something we can extract from the transition function.
Why is the Berry connection flat?
Berry connection. Why this is Berry connection flat? Yes, I guess I'm saying this can have a winding. It is along the S1. So it counts as a winding number. Must be integer, yes, yes, because it's a winding. Yes, that's right. Yeah. Another way to say this is that you have a, in this picture you have a, you integrate over f, but if you patch, you can integrate f within the patch, but you can do the integration, the Stokes theorem to push this integral to the boundary. And if there's non-zero Chan number, that is reflected by this one-dimensional integral you reduced to the original one. Okay. So this is just a quick review of what we want to do, overview or preview of what I want to do. Is there any question for this? Okay, it's okay. Okay, yeah. Yes. Mm-hmm. Right. So f is over m, but we do this by doing patching. So f plus u beta f, and then for each patch, it's smooth and it's dA. So I do integration by part. So du alpha a, maybe there's minus sign because of orientation, a du beta. But this is a from the north patch. This is the a from the south patch. They differ by gauge transformation. So therefore, this is, so let's call this a alpha, a beta. But because these wave functions are related by gauge transformation, a beta and a alpha are related by the gauge transformation. Therefore, this integral reduces to 1D integral d phi, but this is the one-dimensional integral, so therefore this is 2 pi times integer. Yeah, sorry, I kind of mumbled on this, but this is a precise relation between Chan number and then this phase ambiguity. But anyway, this is the idea which goes back to, I think, at least in physics context, Wu and Yan, to describe magnetic monopole. Yes. So, okay. So now we want to do this generalization. So in quantum mechanics, I have a wave function for a particle, and they have a very connection A. This is one form. And then we have the curvature dA for F, which is two form. And then topological classification is given by Chan class. I'm going to discuss one-dimensional, well, 1 plus 1-dimensional quantum many-body system. So it has a tensor product Hilbert space. Tensor product structure, Hilbert space structure defines, let's say, on one-dimensional lattice quantum systems. Or it can be quantum field theory. So this X Um, um, oh, that's right. Tensor product test, is it necessary? Yeah, good question. I may not need tensor product hero space. That's right. I may need locality in some sense. That's right. Thank you for that question. And then I have some state psi of x, but this is now a many-body quantum state. And then I'm going to use tensor network representation for this many-body quantum state. And then the Berry connection now is generalized to higher Berry connection. It's a two-form connection, higher Berry connection. And then there's associated curvature. Curvature is now three-form curvature. Okay. Yeah, so I can write down some Hamiltonian, but you have a one-dimensional lattice quantum systems, and then each term, maybe not each term, but some part of the Hamiltonian just depends on the parameter. And then topological classification is given by the higher cohomology group, H3 of MZ. So this is called Diximier dual D cross. Dual D cross. Okay. So they will come up. Okay. Okay. So let's talk about one D many body quantum systems. I will first work with tensor network representation. So specifically, I consider gapped and then translational invariant. Then non-degenerate ground state, we usually call it invertible. Then forgot, is there anything else I should say here? Yeah, okay, for now that's it. So I have to, because 1 plus 1D many-body ground state, there are many. There are many varieties, but I will limit myself to gapped ground state, which is translationally invariant. I guess translation invariant in some sense necessary, maybe to discuss gapped. And then I don't allow myself to discuss degenerate ground state. So for now, it's just a non-degenerate invertible quantum state. I guess people may call this short-range entangled state and so on and so forth. Yes.
So this must be over the full parameter range.
Yes.
Okay. So,
Yes.
So there's no.
Yes.
It's not a single point where something.
Yeah. So something may happen outside of the parameter space, for example. But yeah, this has to be true for anywhere in the parameter space. Okay. Okay, is this a thing clear? So the convenient framework to represent such ground state is the tensor network framework. So I'm going to use a matrix product state. So I have a quantum wave function which is defined on this one-dimensional system. Maybe I have a spin, something like spin variables, S1, S2, S3, and then so on and so forth. So my wave function is written in this basis. Each may be something like a Q dit. Then I have my wave function can be expanded in this basis. So my wave function may be written in this form. where psi has many indices. We can visualize it as a big box with these legs, which represent these physical degrees of freedom. But this is generic. I'm just writing now generic state. But for this class of state, we can faithfully represent such state by sort of dividing this psi into smaller pieces. I have now a tensor with 3 legs. But I also introduce this additional bonds, which represent sort of virtual degrees of freedom. So this is a matrix product state representation. I think in the equation, we can write psi as A I j j k and so on and so forth. S1, S2, S3, and so on and so forth. And then mostly, I will work with infinite space. Okay, so this is, I take thermodynamic limit. Okay, so this is my class of state I'm interested in. So these states are represented by particular kinds of matrix product state, which represent invertible, translational invariant, invertible ground state in infinite lattice. Yeah.
I know there are a lot of tensor network experts, but here we're summing over all the indices.
Oh, that's right. Yes. So the repeated ones, they are summed, and the S2, they are also summed. So I can also write IJ and so on. So yeah, everything is summed because I don't have anything on the left hand side. Thank you.
It's a single tensor.
It's a single tensor, yes. So I have this setup where A depends on parameter. Yes. So I have right now A, which is a set of matrices because I have physical, right? So maybe I can write this way. Okay, so there are some conditions I also have to talk about because this is MPS, but specific to this particular setting. So there's some more things I have to say for the nature of this A, but roughly speaking, at each point on the parameter space, now I have a quantum state which depends on X, but which means I have a MPS representation of psi. So my MPS matrices depend on this parameter X. Okay. So so that's how we define parameterized family of these gaps, translationally invariant invertible state. And then is there anything, for example, we could ask, is there anything topological about this family? Is there any distinct, topologically distinct family of such states? That is Prof's question. Yes?
So the ground state might be not
Gapped ground state. Gapped. Yeah, so with suitable bond dimensions. Yes. Yes.
Well, you can
Approximate, yeah. It's close, yes. So you can, for a given error, you can tolerate, you can find appropriate or optimized A. Okay. Yeah, that is a question. So I have to ask this aspect, how we discuss infinite lattice. That is somehow crucial. For example, when we're discussing something like this, we are taking inner product. So question is, how do we define inner product, and how we take thermodynamic limit? How do we incorporate? It cannot be exactly. Well, sometimes you can write exact matrix product state, but for these systems, so yeah, even for the family, we can sometimes write down exact matrix product state representation with given bond dimensions. Sometimes we also have to, the interesting kind of detail is that sometimes you also have to change dimension of the Barter space as you move around parameter space. But anyway, sometimes it's possible to write down matrix.
So you're looking at gap translation variant invertible, basically SPTs now.
Yeah, something like SPT. So it is definitely true if I fix, if I'm just interested in given point, this is definitely true. And then question, I think question you're asking, how do I know if something like it is still true as I change x? That's a bit more delicate question. And then I think, okay, so I don't have anything rigorous to say, but many examples where, I know where if this class is something like a Zn, Zp, finite abelian group, you can fix the bond dimension to be somehow large enough, and it can cover entire space. But if this is integer, you can still cover, but you have to change the bond dimension from each patch. And then it's not like I have a proof, but models we looked at, this is. And then maybe one more thing to say, that people also do DMRG on this. And in DMRG, dimensions are, I don't choose this by hand, computer choose, and then it still works. Yeah.
Maybe I can so all these states actually have a local component which is the exact ground state. For instance, maybe yes. So that's why
That's right.
in that sense it is physical. It's just of course a very fine tuned. But all of these actually have the exact ground state of the frustration of the it's called parent.
Right, parent Hamilton, yeah, that's right.
But so there is something like look at this class of states because they are one-to-one correspondence with ground states. So there is still, from a purely mathematical point of view, something missing here. But it turns out that every statement that has ever been made about by looking at this class turns out to also be very general, and this is exactly what Ogata did. Ogata, she visited here, and she has been able to translate these statements and say, oh, hey, let's assume that we have
right.
but now let's relax that. And she has been able to lift these arguments to the complete general case. Okay, so it seems that this is a very good playground for understanding the physics. From the pure mathematical physics point of view, this is not completely satisfactory because of course the exact ground state is not like that. But it turns out that there's no surprises if you actually go to infinite dimension. There's nothing that really happens.
Okay, the questions. Okay, so there was a question about thermodynamic limit. So let's first discuss inner product. Inner product. So I'm going to use kind of simpler notation where instead of writing these boxes many times, I just write it as just like this, just to simplify notation. So physical quantities may be looking like this. So for example, if you are interested in something, some local operator, expectation value of some local operators, in terms of tensor network, it looks like this. And then there's some operator inserted somewhere. And then as I take thermodynamic limit, there are infinitely many these vertical lines. And then one may also worry the norm of state will be a bit dangerous to discuss. But I think a physicist approach to this is that we consider transfer matrix. So let's look at this small piece. So this part looks like this. So I think if I write A, it is combined in this way. So it has the tensor with 4 legs, but you can also look at this as the transfer matrix, taking input from either from the left or right, and they transfer this state to the right or left. Okay, so this type of physical observables, you can consider this part is the transfer matrix to power n. Yeah, let me just do this for the inner product where just O is just 1. That's a special case. So if it is an inner product, this is a transfer matrix. So then something like a non-modular state looks like I have this tensor, the transfer matrix T to power n, and then I make n very large. So for this class of state I'm interested in particular invertible state, there's a unique largest eigenvalue of T. So in the thermodynamic limit, only the most dominant one survives. So I will look for the eigenvector of T. So this is T. But I multiply some state either from the left or right. So I write this way. So this is like a multiplying some vector from the right. I think right and left is always a bit confusing, but I think in the board it looks like right. So then I look for the eigenvector of T. Then there's some eigenvalues. Okay, but as we do some, there's a similar thing for the left. Okay, and then the same eigenvalue, lambda. So multiplying a transfer matrix many times, only the eigenvector with the largest eigenvalue survives. And then by some normalization, we can take the largest, unique largest eigenvalue to be 1. This is some normalization we could do. So in this case, only the largest eigenvalue survives. So we define some dynamic limit by capping off this diagram by the eigenvector, left and right eigenvector. Because as defined, there's 2 dangling bonds here, another 2 dangling bonds here. So I'm saying this is like an inner product, but this is not even a number because there's dangling bonds. But using dominant eigenvectors, I define, so this is definition, define my inner product by capping off this diagram by the dominant eigenvectors. Okay, so I will take n to be very large, but now applying this eigenvector equation one by one, I can remove T because each time T acts on the eigenvector, it's just vanishes, and then only the eigenvector survives. So yeah, so using this eigenvector equation one by one, you can reduce this ranks one by one because eigenvector is 1. So in the end, this is just inner product between left eigenvector and then right eigenvector. T just annihilates. You can just sort of crush this. Okay, so I'm using these diagrams. I hope this makes sense. I think it's just easier to write this way because otherwise I have to write many indices. Okay, so I hope, but sometimes it's confusing, so I hope this is clear. Anyway, idea is simple. To define thermodynamic limit, we use transform matrices. And then in the end, something like this inner product or other physical observables, it's written in terms of the eigenvectors of transfer matrix. Okay. Yes. Yeah, later we actually see it's sometimes it's complex, but here it's real. What is the particular condition? That's right. That's one way to see it. That's right. That's right.
Transfer matrix looks very similar to the so-called boundary tube algebra. Does it have any relation with that?
Yeah, so later part of my talk, I will relate this to boundary CFT context. It's not the boundary tube algebra itself, I think. Yeah.
Even though it's 1D, but it looks like you have the boundary tube algebra.
Yeah, I think you may need additional line to discuss maybe tube algebra, but we can discuss. I think it shows up. For my talk, it's not necessary, but for example, some of my collaborators discuss this in the setting of non-invertible symmetries, something naturally arises tube algebra. But today I don't need tube algebra. Yeah. Other questions? Okay. Okay, so this is like a warm up. So now we can discuss this thing we want to discuss. So I have MPS representation A of x at each point on the parameter space. But anticipating some so like here, sometimes we don't have a single smooth choice for the gauge. We anticipate such thing, so we start patching this parameter space. It's not a bad idea to patch. So I have a patch U alpha. I may have a different patch U beta. And then for a given patch, A of x or MPS, it has smooth dependence on x. Smooth dependence on x. And then we mix many patches to cover this parameter space M. So we are going to discuss what happens when these two patches meet. So I have an intersection U alpha, U beta. And then we're also going to discuss triple intersection where I have another patch gamma, and then these three patches meet. So, but let's first discuss what happens when two patches meet. Okay, so when two patches meet, maybe I don't draw the third patch yet. So when these two patches meet, I pick a point x in the intersection. And then similar to this situation, now I have a two matrix product state. And then these two matrix product states represent physically the same state. So that means I have a 2 MPS representation A alpha x, A beta x. So they look different. They are different MPS matrices, but they should represent physically the same state. So I have, maybe I write this as a picture like this. These are different tensors. But there's something called fundamental theorem in the theory of matrix product space. So if these two matrices, MPS matrices, represent same physical state, they have to be related by this relation. So A alpha of S, A beta of S. There is this matrix G alpha beta. And then, yeah, I think generically it's a similarity transformation, but by normalization, I can put this dagger here. So I use this dagger version. So these two matrices must be related by this relation. And there's also the phase here, some overall phase here. So in equation, there's another tensor here, G alpha beta, G alpha beta dagger. So if these two MPS represent the same physical state, they have to be related by this relation. You can easily check that if they are related this way, as we plug these MPS matrices here, G cancel pairwise. So clearly they represent the same physical state. But converse is also true. So these two MPS must be related by this relation. E to I phi is just the same phase as this. It's just overall phase. So it exists there, but for my purpose, it's not the most interesting part. This is the kind of phase we already know. But this is a new gauge ambiguity which appears because of the MPS representation. So I may call it MPS gauge ambiguity. So this is a new gauge structure which appears in many body quantum states. So this is quantum mechanical phase ambiguity, but there's additional gauge ambiguity. So new gauge structure may have consequence, like the phase ambiguity in quantum mechanics have the consequence to define, to distinguish topologically the different families. And we have a new gauge ambiguities which we need to discuss. Okay. Any questions? So this is what happens at the double intersection. A double intersection, we find these two MPS, they are related by this relation. Okay. It's unitary, but what is important is that phase part does not appear here. It's a projective unitary. Okay. Okay. Now we can move on to triple intersection. U alpha, U beta, U gamma. And we pick a point. And then I have now 3 MPS representations. And then all these MPS representations, A alpha, A beta, A gamma, they have to represent the same physical state. Okay. But now we have this, we know this relation which relate two MPSs pairwise. Okay. But now we can do the same thing. So we start from A alpha, and then A alpha is related to a gamma, because this is the intersection of U alpha and U gamma. So it is related by this matrix G alpha gamma. Sorry, A gamma G alpha gamma dagger. Yeah, by the way, I may be calling this the transition function, right? Like we use the same terminology for the quantum mechanics case. So there's a transition function G alpha gamma, which relates A alpha and A gamma, and then this phase is the regular quantum mechanical phase, which is there, but for simplicity, I just drop it. This is not the most important part. So the MPS gauge transformation relates A alpha and A gamma in this way. but you can also relate A alpha to A beta by using transition function G alpha beta. And then you can also relate A beta with A gamma by using another transition function, so G alpha beta. Now this is A gamma S, G beta gamma, then G beta gamma dagger, G alpha beta gamma dagger. And then we compare these two results. This G. Yeah, so this is defined for the intersection here. But this one is defined for the intersection here. Yeah, so that's why they have a different indices. Mm-hmm. Yes.
Different.
Yeah, transfer matrices are different, yes. Yeah. G prime. Sorry, this is not a matrix in the sorry. So this is the just G alpha beta itself is a projective unitary transformation, and then yes, that's right. So they are just different, like you said, G and G prime, but I'm using alpha gamma and alpha beta to denote they are different. And then we compare these two different representations, and then of course we look at this part. We look at this part. So A alpha is related to A gamma by two different ways, but they should be the same. So one may say, okay, this must be like this. However, the phase is ambiguous. So we can put phase here by alpha beta gamma. Okay. So this is the phase ambiguity associated to this transition function. So sometimes people call this a ambiguity of ambiguity, because G is ambiguity of A, but phi appears in this way as ambiguity. So just like phi was the ambiguity of psi, and then G is the ambiguity of A, but e to I phi alpha beta gamma is the ambiguity of ambiguity. Okay. Anyway, this is just a word. So there's a new data which appears here. That's E phi alpha beta gamma, and it's defined for the triple intersection. Okay. So just like E to I phi E phi alpha beta, from here you can construct the topological information. This transition function with this phase defines the topological information of this parameterized family of MPS. So this defines, as you can see, there's additional index. So therefore, as it turns out, this is related to the third cohomology group.
How many different patches you need?
I do not have any a priori knowledge, even for the quantum mechanics case, I think. Okay, this is not written in that way. we don't know a priori how many patches we need, but we need to assume okay, I don't know if there's a convenient way of knowing it, but this is how we formulate. That's right. So the simplest example we had, we had the parameter space where M is S3. Just like simplest example for the Chang class is where M is two-dimensional sphere, which sort of covers the Dirac monopole. Now we have a simplest example where parameter space is S3. I'm not sure this is the most simplest, but anyway, example we have, for example, is where M is S3, and then I have to patch S3 into 4 regions. I think it's minimal, but from that perspective, I guess we don't have a convenient method to determine. Okay. Yes, because of the co-cycle conditions, so it just vanishes. Similar co-cycle condition appears for the 4 intersections for G and so on and so forth. That's right. So yeah, phase does not, quantum mechanics phase does not affect this one. The number of patches. Yeah, number of patches, I don't know. My genius collaborators came up with number 4. And then, but once again, I think even for the quantum mechanical case, I think a priori, yeah, maybe in quantum mechanics example, it's always, yeah, so sorry, I don't know. I don't.
It must be an independent property of the manifold. So given this manifold, this determines.
That's right. So I think for the quantum mechanical case, we know one Dirac string would be enough usually. And then I just need to find a patch to avoid Dirac string one way or another. And then, yeah, okay. I don't have any intuitive things to say here. But this is theoretically convenient. Most practically more convenient way is to in fact define curvature. And then I can just integrate over curvature to define topological invariant. But this is kind of convenient for theoretical discussion. Okay. 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 So I think I'm kind of late, a bit late. So okay, I have still some time. So let me discuss important ingredients. So in quantum mechanical case, once again, it's this example. And then I have phi alpha and phi psi beta. They are related by this phase. But equivalently, we can extract this phase from the inner product. So I want to define proper inner product so that we can extract this information we are discussing. But since this space has 3 indices, phi alpha, beta, gamma, the way we found was to use something we call triple inner product. Which is the inner product or generalized version of the inner product defined for 3 many body state. So we define this triple inner product in the following way. So I take 3 matrix product state, A alpha, A beta, A gamma. And then let me start with A alpha and A beta. So I take the partial inner product between A alpha and A beta. So the part of the tensor network of A alpha, they are contracted with the part of the tensor network of A beta. But there's these dangling bonds. They are not yet contracted. Then I take the third matrix product state, and then I contract this way. Okay, so there's 3 states now. They are contracted in this way. So this is like a generalized version of the inner product, where for inner product, it only takes 2 states, but now it takes 3 matrix product states. So this is a kind of, I don't know if it is called inner, but this is a kind of product we can define because of the extended nature of tensor network. In quantum mechanics, you cannot define partial overlap, but we can define partial overlap. That's true. That's a good question. I don't know. Yeah, so what is hidden here is that tensors here, they are A. And here it's a conjugate. So I can also use the dot. It's here, it's A, but I think strictly speaking, I have to put star here, sorry. So there's a conjugation coming here. So there's a conjugation also coming here. But for gamma, it is partially conjugated. So anti-linearity, it's certainly perhaps antilinear when pasting a beta, but something like a gamma, I'm not entirely sure. But that's a good question. This partial conjugation, some people think it's a bit weird, but it somehow arises naturally. We can also take 4 states to avoid this partial conjugation.
So the position when you take this intersection, since the translation invariance.
That's right. It does not depend, yes. Yeah, so segment and then periodic boundary conditions. Currently, we do not know how to do this calculation. That must be position dependent, I think. But yeah, so possibility is, once again, we didn't know how to make this work for finite case and then periodic case, but it's possible that phase part may not depend on X, for example. And then in that case, phase information, if it is topological, it can be still extracted by inner product, which is X dependent, but then this position dependent, but amplitude part, for example, may depend. Okay, that's just a wishful thinking, but once again, we don't know. Okay, but then this diagram can be evaluated by using similar idea. So I have an infinitely many horizontal lines this way, infinitely many lines in this way. But I have to take thermodynamic limit. So I cap off this diagram by the eigenvectors of transfer matrix. I don't think we don't. Yes. Yeah, here we don't do this, but I know what you're saying. Yeah, it may make more sense if it's a time reversal symmetry. Yeah, I guess we don't need time reversal symmetry. So using this calculus, once again, I have many transfer matrix here. I have a product of transfer matrix here, but using eigenvectors, we can reduce this diagram to a very simple diagram, only in terms of the eigenvectors. But now there are 3 eigenvectors. And then, as it turns out, this is exactly I alpha beta gamma. So this is how we extract this. Analogously to this, we can extract this topological phase information by using inner product. Okay. Okay. So I have not much time left to discuss field theory part, but once we got here, we basically somehow transport this formalism to quantum field theory formalism. But sorry, I skipped many details. So if you have questions, please ask me. Okay.
So this picture, the idea would be, I guess, that this picture also would be true if you would take infinite ball dimensions, the exact.
That's right.
Ground states. That this has nothing to do with them. Yes.
So that's right. So something like this partial conjugation.
Well, if you can define that, then you would have it for any function.
That's right. That's right. I mean, I'll be happy if everything is completely independent of the MPS, then it's better situation. But I cannot separate right now from this formalism from the MPS specific things.
Because you need a partial.
And also maybe transfer matrix, but
No, but that should be.
it should, you think it's fine? Okay. Yeah. So I mean, I'm happy to discuss how general this is. And then right now I'm using MPS, and then I'm happy if I could say something more general. In one sense, I'm trying to formulate this by using field theory because I want to somehow go beyond tensor network framework. But yeah, I don't know. But this partial conjugation, I know how to get rid of. But other part, I'm not sure if I can completely get rid of MPS specific consideration. So I'm happy to discuss. Okay, so sorry, I think I didn't have much time to discuss this part. But along this way, I'm using tensor network to define, formulate the higher Berry phase. But in some sense, it's enough in practical sense because in 1D many-body states of the type we're discussing, MPS is a very good framework anyway. But still, one may want to see how higher Berry phase can be formulated without using tensor network. So we decided use boundary conformal field series to discuss at least some of these ingredients we just discussed. So yeah, so let me just remind you. So it's a conformal field theory with boundary. But usually conformal field theory describes critical states. So, but we are discussing gapped states. So why CFT or boundary CFT in particular? Why they are relevant? So idea is to take boundary as some sort of initial state. So I'm here. Okay, so I'm kind of thinking this is the direction of time. This is a space. I mean, for field theories, maybe it does not matter too much, but yeah, let's say here I have a time-like boundary at some particular position x, but you can also exchange space and time such that now this direction is taken to be a time direction, and then this region is a conformal field theory, so there are Euclidean time evolution defined by conformal field theory Hamiltonian. In equation, this is a state which is the smeared boundary state. So this is boundary state which describes this initial condition, and there's the Euclidean time evolution. So it is known that this type of state can describe short-range entangled state. For example, Cardi and Calabrese use this state as the initial condition of quantum quench, and so on and so forth. And then this type of state was also used to discuss 1+1 SPT phases and so on and so forth. But anyway, unlike the ground state and then primaries of conformal field series, this is the short-range entangled state, short-range correlated state. So this is quite suitable type of state for our discussion. This is a critical Hamiltonian, conformal field theory Hamiltonian. Okay, and then beta is some sort of smearing parameter. So measured in terms of the CFT Hamiltonian, this state has infinite energy. So it's kind of convenient to smear it, but it still have a finite correlation length set by beta. So this is short range state.
So B itself has zero correlation.
Zero correlation length. I don't know how to define it, but it's super ultra short range. But beta somehow smeared it, broadened it a little bit. Okay, so this is a convenient continuum state we can write down using conformal field theory Hilbert space to represent some short range correlated state. And then if there's a parameter dependence, we should be able to discuss higher Berry phase. So we can discuss parameter dependent family with this smearing, but I'm not writing down smearing part explicitly, but this is the family of boundary state or boundary condition in conformal field theory, which depends on some parameter x. In the paper, we call it a boundary conformal manifold. Boundary conformal manifold. There's similar terminology for the bulk CFT, where you can change marginal parameters continuously. So, but this is a boundary version. So we have a boundary conformal manifold. And then, is there interesting topological distinction for such family? Maybe forgetting. This is conformal boundary. After sorry. After regular, it's not strictly, but B itself is conformal boundary. Yes. Okay. So this is a setting we are interested. And then once again, since it is short range, they are short range correlated state. Generically speaking, we should be able to discuss some of these things we are discussing. But now we don't have a tensor network formulation. But to make a long story short, we sort of see very close analogy between tensor network formulation and then conformal field theory, boundary conformal field theories. For example, we can discuss inner product. So inner product in picture looks like this. I have two boundary states, maybe B alpha and B beta, and then they are bra and ket. And then there's this smearing factor, maybe 2 beta H. So this is the path integral, which represent inner product of two boundaries. That's right. So here I'm changing formulation a little bit by taking these two as two physically distinct states. Yes, thank you for this comment. We can also do the same thing for tensor network calculations. But here, yeah, like Frank said, these are not physically the same state with different cases. Here, they are two physically distinct states. Okay. But now we are interested in this path integral. So this path integral is analogous to this diagram. We have two matrix product state. Once again, in the previous discussion, I take this to be the physically the same, but similarly, we can also take two physically distinct matrix product state, and then there was the eigenvectors of transfer matrix, which is capping off this diagram. In boundary conformal field theory context, these two boundaries, they meet at infinity, and then there is the you can sort of define operator which changes boundary condition from alpha to beta or beta to alpha. So two different, yeah. So that's right. Maybe I should write x alpha, x beta. That's right. Yeah. Sorry, I have not defined yet, but yeah. That's right. So these states are, I don't know, generated by considering exact marginal boundary deformation. So it may be looking something like this. Some coupling constant psi alpha x, and then psi is the, so this is the one-dimensional boundary of the two-dimensional space, and then this is the perturbation or coupling which appears only on the boundary, and they're exactly marginal. We are interested in exact marginal deformation. Exactly marginal deformations. Okay? And I take two such state, but with different coupling constant. And then when these two boundaries meet, there is the local operator or boundary operator, which is inserted at the domain wall between these two states. So this boundary operator, or boundary condition changing operator, we found that we think that this plays a role of this eigenvector of transfer matrix. And then with this identification, we can also define a triple inner product. So this is the inner product, but we can also write down triple inner product using boundary operators. So I drew this picture before in this way: 3 MPS, A alpha, A beta, A gamma. But topologically, you can think of this as some sort of disk. Yeah, this is the conformal field theory equivalent. So I can consider disk. And inside the disk, there's a CFT path integral with Euclidean time evolution, E2 minus beta h, where h is the gapless CFT Hamiltonian. But on the boundaries, there are three. So in the tensor network picture, there are three eigenvectors sitting here, which sort of connect these two patches, two MPS, these two and these two. Similarly, in conformal field theory, we consider partition function with these three operators inserted: alpha, maybe B alpha, B beta, B gamma.
Partial conjugation?
Yeah, so if I draw this way, so this looks like, yeah, so if I do this way, so alpha, and then, yeah, I think I understand. Partial conjugation is somewhat complicated thing. Let me think. It is complicated, but we think it does not matter. Okay. But I cannot say in a very simple way why this is so. Okay. So in the end, we think we can compute this disk partition function in conformal field theory with three operators, three boundary operators inserted. So this is how we formulate it. Any more questions for this? Okay. Once again, I may be skipping many details, but it seems at least intuitive enough, I hope. That's a phase, yes. So we compute this. Yeah, let's say I parameterize this circumference boundary by theta, and then beta gamma delta theta 2. So this is the partition, sorry, the correlation function on the disk. So there's the amplitude part, which depends on the chord distance between these operators, like sine theta 1 minus theta 2 and so on and so forth. But there's the overall phase part, C alpha, let's call it C alpha beta gamma times all the distant dependent part. So we are interested in this phase part. Okay. So this is the analogous thing for E, I, phi, alpha, beta, gamma. And then we formulated higher Berry phase in BCFT context this way. And then final thing I want to mention is that we looked at various examples. So we looked at, for example, the boundary state of SU2 level K versus Witten model, referencing by your paper. So for example, in the SU2 level K versus Witten theory, there is a family of boundary state which takes this form. Sorry, maybe here I'm kind of using the CFT language, so I'm sorry if you don't know this. You're not familiar with this formulation, but I'm writing down the defining equation of boundary state B of G, which depends on this parameter G, which is basically SU2 matrix. So this is a boundary condition. So this boundary condition defines the family of boundary state. So there I have to remember. So yeah, so basically, the moduli space of this boundary state is S3 or RP3. I write it M. My parameter space is either S3 or RP3, mostly a S3. But when the level of Witten theory is even, and then there's some representation I have to put. But anyway, if I take particular SU2 representation, K over force representation, there's some identification which happens. Anyway, mostly this is just S3 or RP3. And then for this case, we can compute higher Berry connection as well as higher Berry curvature by evaluating these 3-point functions. Okay. Either way, we found the so it depends on the so usually S3, but there's a okay. So I have to put this depends also on the representation. So I start with Cardi state with representation J, and then but as you change this parameter G, two antipolar points are related by B, G, let's say J, and B at the antipolar point, let me put this, is related by this relation. So mostly, if this, sometimes this J and then this J coincide. In that case, as you change parameter on S3, at the antipolar points, sometimes your state goes back to itself. K over 2 invertible representation. I don't know what it means. Yes, that's right. Yes, yeah. So in that case, we have to identify these two antipolar points. So that's why sometimes mostly just S3 because you are changing this SU2 rotation matrix, but sometimes there's a funny identification happens. In that case, we computed higher Berry connection curvature and the integral of higher Berry curvature, which is quantized. Another example, which is perhaps somewhat more interesting. So this is the last thing I want to mention. So the last thing I want to mention is another example where I have a continuous family of boundary state for compactified boson theory with the center charge is 1 with radius which is at some rational value, P over Q. Just sometimes some people put 2 here, but this is the convention my collaborator prefers. So I'm just writing as a rational radius as a rational way. So anyway, we pick a particular radius for this equal 1 conformal figure theory and have a family of boundary state. In this case, the moduli space of boundary state is an obifold Zp plus dq. Okay, and then we just focus on the case where p is n, q equal 1. In this case, moduli space is SU2 obifold with Zn. So this is another example we looked at. So this is an interesting example because parameter space is not a manifold. It has an obifold singularity. In this case, we found the integral of 3-form flux is fractional 1 over L. So this is integral over n. We computed 2-form and the 3-form curvature using this formula. And in this case, there's a fractional quantization 1 over n. It's a bit like getting fractional quantum Hall physics in my mind. Maybe not exactly, but because of obifold singularity, we can also get fractional value for the integrated 3-form curvature. Okay, maybe this is the last thing I want to say. So thank you very much. And then I'll take any questions. Okay, thank you.
Closing to this computation, it's the you need to know the conformal dimension of the boundary changing operator.
Yeah, so mostly we could just do perturbation theory because so this is something which is defined for when alpha, beta, gamma are very close to each other. That means these coupling constant, marginal coupling constant sort of jumps at the location of these operators, but they are very small. So you could do perturbation theory. So that's a technical simple calculation we could do. Okay.
So, but is there also a trickle cycle related to this C in your boundary CFT, or is it the same?
Yeah. So this is mostly 2 cocycle, but you're right. So this type of thing is related to 2 cocycle. So for example, something I did not mention, we could also take SPT phases, and then you can put 1 plus 1 the SPT phases, and then you can go to different MPS gauge, and then you extract 2 cocycle or SPT invariant of in 1 dimensions.
My question is actually what the relations between the second part of the
Mm-hmm.
that is C alpha and the boundary CFT case
Yes.
has the same meaning as this angle in the MPS case.
Angle.
Well,
Oh yeah, phi. Yeah. So yeah. So once again, slightly different because of what you asked me. So in the MPS case, there are 2 versions where we take physically the same state in different gauge, or we can also take 2 states which are slightly physically distinct. And then I did not mention that version, but that version also works. In boundary CFT, I do not know what do I mean to have 2 boundary states in different gauge. So mostly I'm just taking 2 states which are slightly physically distinct. It's perhaps interesting to ask what is the meaning of gauge in the BCFT. Uh-huh. Yes.
Could it be that what you're saying somehow you have different relevant deformations of the same CFT that flow to the same point?
Yeah, I'm not entirely sure what you mean, but that's right. That's right. Right.
Follow the flow on the bottom of the board.
Maybe I will. I'd love to know a bit more about this, but yeah. Good question. Sorry. Yeah.
Maybe I'm asking the same question again, but in nuance. But in the earlier part, it looks like this triple inner product in the MPS case is calculating just like check homology of your moduli space. Do you expect that this CFT triple inner product thing is calculating check homology of, I don't know, the moduli space boundaries?
Yeah, this is more like the I'm doing more like a differential form version, like integrating over 3-form curvature. So to get check version, I may want to know what do I mean to have, yeah, it's related to this question in fact. So it's not a check version for boundary CFT. I don't know how to do this for the BCFT. Yes. Okay.
So don't you ever get level crossing or like generate ground state somewhere on M?
Sorry, which level crossing we're discussing now?
So you wanted to have your boundary conditions sit close to each other.
That's right. Yeah, so we don't allow level crossing in our formalism. There's always a unique lightest state which changes continuously. That's our assumption. Yes.
Two boundary changing operator, like take the overlap of boundary states. Is there some data there also?
Yeah, so that would be regular Berry phase, but I think, yeah, so we also try to formulate the regular Berry phase this way, but I think we found to get something interesting there, I have to put additional line operator here. Then you can interpret this as the regular Berry phase, which appears. Yeah, yeah, I'm not entirely sure, but I think something like that should be true. That's yeah. It also appears at the regular in a product.